Hi guys, welcome to our channel of Sciences and Mathematics. I'm Ernest. Today we're going to look at the concept of one of the applications of enthalpy of formation. Of course, we have already discussed this particular topic in some of our videos that I'm going to put a link in the description box below. So in this case, we're going to see that the application of enthalpy of formation can be achieved using a different strategy. Now in this case, this strategy that we're going to use, of course, we had talked about the concept of energy level, the thermochemical cycles. For today, we're going to use the dissociation energy for particular bonds, and we have selected a range of three particular kind of bonds that I've given on the board. I'm going to give a relevant expression for a stoichiometric equation for the formation of a particular compound, which of course is going to use the concept of the bonds that I've illustrated on the board. So in this case, of course, we are going to see how we can be able to find the resulting energy given the bonds energy that I've given on the board. So that's it for this particular discussion. And in this case, of course, we're going to see that apart from the thermochemical cycles, the energy levels that we talked about, and the Hess law of summation, this concept of dissociation energies of bonds can, of course, be used in addition to those particular procedures. So for today, I'm going to use the concept of formation of one of the compounds, that is HCl. So that's addition or maybe a combination of hydrogen plus chlorine to form HCl. So this is a gas. So we said for us to achieve this concept of stoichiometry, we have to write the states of these reactants and the product, and try to see that the reacting volumes have been balanced appropriately. So we'll have to to balance the equation for the hydrogen, the reacting hydrogen and chlorine. So therefore we have a stoichiometric equation for formation of HCl. So basically we're going to use the bond dissociation energies that I've provided on that small table on our right to try and find how we can be able to calculate the enthalpy of formation of this particular compound. Now there's a specific procedure that we need to follow for us to achieve that, and this is a set of around maybe 4 procedures or 4 basic procedures or steps that we need to do in order for us to appropriately apply this concept of dissociation energies of those bonds. So the first one is to write the equation using the structural formula. Structural formula implies, in this case, we talked about the representation of materials or maybe molecules in organic chemistry, and we talked about the concept of line structures, a structural formula for expanded and condensed formula for organic elements, specifically in that particular video. So in this case, I'm going to use the structural concept, which basically tries to show the bonding in those particular molecules. So in this case, I'm going to show the bonds for HCl, the reactants and the products basically. So the reaction can be written as hydrogen, showing this specific molecular bond, plus chlorine, which is going to form 2 molecules of that specific gas. So still we can be able to write the states of these reactants and the product. And in this case, we can be able to identify the bonds which are being broken. Now when a chemical reaction takes place, there are several maybe particular rearrangements of this specific structural form, the structural rearrangement of these reactants in order to form new products. So in that case, we are having 2 scenarios whereby there are bonds which are broken and others which are formed. Now for these reactants, the bonds are going to be broken for that is for hydrogen and chlorine, and we're going to have a bond of HCl that is going to be formed on the product side. So this is a bond formed versus the bond that is broken on the reactants. So these energies of course, of dissociation of these specific bonds are the ones that we're going to use in order to find the enthalpy of formation of HCl. So the strategy we're going to use here is said that we're going to apply the range of around 4 procedures. The first one is to write the equation using the structural formula as I've done. So the second one is to identify all the bonds that have been broken and the ones which have been formed. So this is a second procedure. We've identified the bonds, the 2 bonds have been broken, and for the product side, that bond has been formed for HCl. So the procedure number 3 is to try and figure out how we can be able to obtain the energies for the bonds formed and broken. And in this case, the energies that we're going to identify in this case is I've not given one of the energies of dissociation for HH bond, and this is going to be 436 kilojoules per mole. I've got the units already there, so it's 436. So therefore, for bonds which are broken, we're going to have H bond which is broken. Its energy is 436 kilojoules per mole, and we're going to have another bond which of course is broken for this molecule of chlorine. So its dissociation energy is 242 kilojoules per mole. So for us to find the total energy that is required to break the bonds before that final product has been formed, we're going to have the sum of these 2 energies for us to find the total energy of bonds which have been broken. So therefore the total for that one is going to give us 678 kilojoules per mole. That is for 678 kilojoules for those 2 species of the reactants which are being broken. Now for the products that is formed, so this is a total energy for bonds broken, and I'm going to have another set of energy for bonds which are formed. So basically, which are the 2 sets of HCl. So we have HCl. From the dissociation energies we have been given this 431 kilojoules per mole. So this is 431 kilojoules per mole for HCl. So therefore, for us to have a relationship of the energies which have been has been used in that bond breaking and formation, we're going to have still to find the sum of the energies of the bonds which have been formed. So in this case, from a stoichiometric equation, we have 2 volumes, or maybe using these coefficients for moles, we have 2 moles. This is for a single mole, kilojoules per mole. So for 2 moles which have been used in this stoichiometric equation, we're going to have to multiply this specific value for this by a coefficient of 2. So this is 431. And this is going to give us 862 kilojoules for those 2 moles which have been formed for the product. So therefore, we're going to have the total energies used using those 2 specific values by finding still the sum of those 2 energies. But when we were talking about the concept of endothermic and exothermic reactions, in our discussions we mentioned that the concept of bond breaking is an endothermic process. So I'm going to do away with this. So we have bond breaking for the reactants and the bond formation. So basically these are for the reactants and these are for the product. And we have found those 2 specific the values for those 2 specific instances for bond formation and bond breaking. First, so for bond breaking, we have a total of 678 kilojoules, and then for bond formation, we have 862 kilojoules. So I've mentioned the concept of exothermic and endothermic reactions, and the process of bond Now the process of bond breaking and bond formation is going to be assigned those specific concepts for endothermic and exothermic reactions. So as we can see on board, maybe from the process of or the concept of fusion, we know that during bond breaking and bond formation, so if we have a bond between hydrogen and hydrogen, in this case, this molecule is going to take in energy, and we from the concept of the kinetic theory, the molecule is going to attain a very high vibration, or maybe vibration mode, and then therefore we're going to have this bond broken. And during the concept of bond formation, we're going to have these specific molecules releasing this particular energy that it had taken in. So we shall apply the two concepts in this particular concept of bond breaking and bond formation. Therefore, for the first one, we're going to have a location for energies of the enthalpies of those specific signs for the for bond breaking, for positive, and bond formation for negative. Therefore, we can have a perform an operation, a normal mathematical operation using that one in order for us to find the enthalpy formation, which of course is going to be represented as the sum of the enthalpy of bond breaking and bond formation. Now, which can be represented as enthalpy of formation of HCl is equals 678 plus. So the second value that we talked about is an exothermic reaction, 682. So this basically is going to give us the value of that specific calculation to be negative 184 kilojoules. So therefore we can be able to use the same concept of the energies, or rather the dissociation energies of these particular bonds for the reactants and the products in order to find the enthalpy of formation in a stoichiometric equation like the one we had written for hydrogen and chlorine, which are forming HCl. So basically this is how we're going to try and figure out how we're going to be able to do this range of calculations in order to find the energy that is associated with this. Now in this case, when we are trying to write this stoichiometric equation, the reacting volumes for this specific kind of reaction is one for the product, but the formation for the HCl has got 2 moles. So for us to cater for those particular set of volumes, the reacting volumes for the product, we can be able to find the enthalpy of formation of 1 mole from this particular set by dividing the value that we have obtained, that one, which is 184 by 2. As you can see, I've intentionally written this one as kilojoules. So basically, which represents the enthalpy of formation of those 2 volumes of HCl. Therefore, we can be able to obtain the enthalpy of formation of 1 mole of HCl by finding 184 divided by 2 as per these volumes, which is going to give us negative 92 kilojoules per mole. So basically, this is one of the strategies, as I've said, that we can use to find enthalpy of formation of other compounds. So I hope this, apart from the thermochemical cycles that we have already practiced on, all the energy levels that we have seen and the Hess laws of summation, we can also be able to use this fourth strategy in order to find enthalpies of reacting compounds, or maybe reacting elements to form compounds. So I hope this is understood, and we're going to apply it appropriately in case we come across a question of the same kind. So that is it for today, guys. Bye, God bless.